Another small concept here is, this is the circuit. These are two magnetically coupled coils. Now we want to find out the equivalent inductance. Okay, so how to find that? The currents directions, if we take as I1 and I2, that means both the currents are flowing into the dotted polarity. Okay, the self inductances are given as L1 and L2, and the mutual inductance is given as M, let us say. Okay, so now this can be drawn into an equivalent T circuit. That means it will be in the form of T. Here there will be one inductance, here one, and here one. So this is in the shape of a T. Okay, another form is the equivalent pi circuit. So that means there will be inductances in the form of a pi. Okay, so this will be the current I1 and this will be the current I2. So that means here if A, B are the terminals, C and D are the terminals, here A, B, C and D. We are simply replacing with an equivalent T circuit in this case and equivalent pi circuit in this case. Now let us name this as LA, this we will take as LB, and this as LC. And the pi circuit we will take the subscript capital L. Okay, here capital LB, capital LC. Okay, so I mean the subscript is in capital letter. Now what will be this values of LA, LB, LC, L1, L2 and L3. Okay, so these both represent the equivalent T and pi circuits. You can write here, and this is the equivalent pi circuit. Okay, so the relation you can derive from the magnetically coupled equations. You can take voltages at both the coil sides and you can write expressions in terms of I1 and I2, but the derivation I am not going to do here. I will write down the final result. So what will be the value of LA? This is given by L1 minus M, LB is equal to L2 minus M, and finally LC will be equal to the mutual inductance M. Okay, then what about here, equivalent pi circuit? Here L capital A is equal to L1 L2 minus M square divided by L2 minus M. LB is given by same numerator L1 L2 minus M square divided by, in the denominator you have L1 minus M. Okay, that means the opposite side. See, LB is on the secondary side, so in the numerator you have L1. Okay, and what about LC? This is going to be L1 L2 minus M square, again it's the same numerator divided by M. Okay, so you can see that this L2 minus M is nothing but LB, L1 minus M is LA, and LC denominator is M, which is simply this LC in the T circuit. Okay, so this is something so that you can remember easily. Okay, one more important concept here is, see, this is a primary circuit. Here we have the primary side here with the dotted polarity. Now on the secondary side we have some impedance. Okay, we'll call it as the load impedance. This is the load side. So we do learn in transformers, in machines we discuss how to refer the primary side or the secondary side impedances towards the other side. Okay, but here we are talking in terms of the mutual inductance. Right? We don't talk about mutual inductance in machines. We talk about the equivalent circuit. Okay, so in terms of mutual inductance, how do we get the equivalent input impedance? So let us take this to be the input voltage. Now we want the input impedance, that means looking through the input terminals. You can use the mesh analysis here. This is current I1 and this if you take to be current I2. When current I1 is flowing into the dotted polarity, this dotted terminal will become a positive polarity. So the current will be driven out of the positive polarity. So I2 will flow like this. Now if you write the equations using Kirchhoff's voltage law, KVL, what will it be? Vs, the first equation, Vs is equal to I1 times Z1 is the voltage drop across Z1 plus the voltage drop across the inductor due to the current in itself, that means due to I1. What will it be? j omega times L1 into I1. Also, due to current I2 in this coil, there will be voltage induced here. So, what will be that current? I2 here, what is it doing? It is leaving the dotted polarity. So, here at the dotted polarity, it will be negative and we are going in this direction. We are writing KVL in this direction. So, we are encountering negative sign first. So, you are going to get minus j omega m into I2 because this is associated with I2. Okay. So, this is equation 1. What is the next equation? The second, in this load circuit, the equation is going to be I2 times ZL. This is the voltage drop across ZL. Now, what about the voltage drop across this? One part will be due to the current in itself, that is due to current I2, and other will be due to the mutual inductance, which is because of the current in the other coil. Okay. So, the self inductance term will be j omega L2 into I2. Now, what about the mutual inductance? You can see that the current I1 is flowing into the dotted polarity. So, here there will be positive polarity, but we are going in this direction. So, that means we are encountering the negative sign first. So, this is going to be minus j omega m I1. This is equal to 0. So, this is the second equation. Now, what do we want? Z input, which is nothing but Vs by I1. The voltage across this and the current that is flowing in. That this ratio will give the input impedance. So, in the second equation, we will write the I2 current in terms of I1. So, this will give I2 is equal to j omega m I1 divided by ZL plus j omega L2. So, this you can substitute I2 in equation 1. So, this will give you Vs is equal to I1, you can take out common, Z1 plus j omega L1 minus j omega m. I2 is going to be j omega m I1 divided by ZL plus j omega L2. Divide the entire equation by I1. Dividing both sides by I1. What will you get? Vs by I1 is equal to Z1 plus j omega L1. Here j into j will become negative. So, you are going to get a positive sign finally. So, plus omega m whole square divided by ZL plus j omega L2. So, this is equal to the input impedance. Now, how to remember this expression? It seems like a pretty complicated expression, right? So, you can see here Z1 is anyways there in the primary circuit. You can see here Z1 is there in the primary circuit, okay? So, you can consider it like Z1 plus the whatever this is there, they are in series. So, Z1 plus something else, okay? So, Z1 is anyways there. So, you can write Z input is equal to Z1. And here also j omega L1, this is the self inductance of the first coil, that also you will have plus j omega L1. Now, the remaining part is only the self inductance of this coil, the mutual inductance part and ZL. So, this part is all combined, you can say, which is written as omega m whole square. That means the reactance of the mutual inductance. Frequency into inductance will give you the reactance, right? Divided by ZL plus j omega L2. So, you can see that once again ZL is the load impedance here and self inductance is the j omega L2. So, you are just adding both of them, but they are in the denominator. In the numerator, you have the mutual inductance, mutual reactance whole square. So, this is how you can easily remember what is the input impedance. It is better if you can remember. Next, we will discuss the energy in a coupled circuit. Okay. So, that means once again you take the two coils which are having magnetic coupling. Okay. The dot polarities, let us say, it is like this. Self inductances are L1 and L2 and the mutual inductance is given by m. Okay, so now the energy in this coupled circuit is given by half L1 I1 square, where I1 is the current in the first coil, plus half L2 I2 square. This anyways we know, right? Half Li square is the energy that is carried by an inductor. Now there is a mutual inductance term as well. Okay, so that you're going to get as plus or minus m I1 I2. So when do you get plus? When do you have negative? Right? So we will see. First I1 and I2 you can write. This is the current in first coil, and I2 is the current in second coil. These are both instantaneous values. Okay. Now when do we use plus and when do we use negative? Plus sign is used when both currents enter or leave the dotted terminals. Enter or leave in both the cases. And when will negative be used? When one current enters and other current leaves the dotted terminal. Okay, so that means if you take an example, let us say this is the coil. Now this is the dotted polarities. This is current I1 and this is current I2. Then what will we use here? Plus or negative? We will use plus because both currents are entering. Okay. Now what if both the currents are leaving? Like this. Then also we use positive. Now negative case, when will it be? When one current is entering and other current is leaving. Then we use the negative sign. We are talking about the positive or negative sign in the energy expression. Okay. So do not get confused. In the energy expression, the positive polarity, positive sign here is used when both the currents are entering or leaving the dotted terminals, and the negative sign is used when one current leaves and other current enters. Finally, the last topic in magnetically coupled circuits is the coupling coefficient. So we will see what this is. We have seen that the energy in a coupled circuit is given by half L1 I1 square plus half L2 I2 square plus or minus m I1 I2. Now if you consider the positive sign, then energy will always be greater than or equal to 0. Only if the currents are 0, energy will be equal to 0. Otherwise it will be greater than 0. But what for the negative case? Half L1 I1 square plus half L2 I2 square minus m I1 I2. This should also be greater than or equal to 0 because this is finally the energy only. Energy cannot be negative, at least in this case here. Okay, it cannot be negative. The inductor will either have stored energy or it will not have stored energy. Okay, it will not have some negative potential energy. All right, so now if this is the case, if there is a positive sign, anyways mathematically we have no problem. But if it is negative case, then what should be the condition? What should be the values of m1, L1, L2 and m such that this will be positive or greater than 0? For that we do some slight modifications. So half if you take out common, we'll try to get the a square plus b square plus 2ab form. Okay, so I1 root L1 whole square will be one term, a square term, plus I2 root L2 whole square minus 2I1 I2 root over L1 L2. So this is the complete square term we can get. A square plus b square minus 2ab. Okay, then you have to, whatever you have subtracted, you have to add again, right? So minus m I1 I2 plus, here this is 2 times I1 I2 root L1 L2 divided by this 2 here as well. So you're going to get plus I1 I2 root L1 L2. Now this is greater than 0. So what will you get here? Half into I1 L1 minus I2 root L2 whole square plus I1 I2, if you take out common, you're going to get L1 L2 minus m. This entire thing is greater than 0. Now this is a square term, okay. So this will always be greater than or equal to 0. So if this entire term must be greater than or equal to 0, this term also should be positive, okay. I1, I2 are anyways positive. We have already taken the directions. So only condition is that root over L1, L2 minus M should be greater than or equal to 0. Okay. So here you will get the condition M, the mutual inductance, will always be less than root over L1 and L2. So this is an important relationship. Now this ratio M by root over L1, L2, it will always be less than 1, and this ratio we call it as the coupling coefficient K. Okay. It gives you the degree of coupling between any two coils. So this is the coupling coefficient. It gives the extent of coupling between the two coils. Okay. So you can write in terms of the flux, K will be equal to the flux that is linking both the coils, right? If this is the coil and this is the other coil, if I1 flows through the first coil, then phi 12 is the flux that is linking both the coils divided by phi 1. Okay. So you can write here so that you won't get confused. Flux, this is the total flux due to I1. This is the flux linking both the coils. Okay. Whereas this phi 1 will link both the coils as well as only the coil 1. Okay. So this is the coupling coefficient, and this will give you the measure of coupling. It will always be less than or equal to 1. Okay. Also, since the mutual inductances and the self inductances, they are all positive values, this term will also be greater than or equal to 0. They cannot be negative. So finally you can write 0 is less than or equal to K less than or equal to 1. Okay. So when will you get 100% coupling? This is if K is equal to 1, then that means all of the flux that is linking coil 1 will link coil 2 as well. What will be that case? That case will be when, consider a magnetic core like this. Now let us say this is the coil 1, then the coil 2 will be just wound over the coil 1. Then whatever flux will be linked with coil 1, the same flux will also be linked with coil 2. That is the case of perfect coupling, and that time K will be equal to 1. The other extreme is that K is equal to 0. In that case, it just means that there is no coupling.